Hello, so in this video we're going to do the fifth question, which is the last question on the 2009 MAT, Oxford MAT Maths Admission Test. So it's the last question, and it's obviously intended to be not necessarily more difficult, although often it is more difficult, but a little bit outside of the norm. Not really based in any way on A-level syllabus, but just on general sort of logical and thinking basis. So the question has quite a big setup, including this diagram I showed here. And it's basically that we've got an n by n grid of squares. So as you see here, we've got a 6 by 6 grid of squares there on the bottom right. And n is going to be any number bigger than 1, and a tour is a path drawn within the grid so that, well, you can read this part yourself, but I'll just continue reading. Along its way, the path moves horizontally or vertically, so not diagonally, but only horizontally or vertically, from the center of one square to the center of an adjacent square. So you can see this particular path moves, if I just choose a different color, from the center of the top left square to the next square on the right, and then it moves from that to that one, and so on and so on. The path starts and finishes in the same square, so that's marked by this black dot here, so that's the starting and the ending point, and the path visits the center of every other square exactly once. So this diagram, if I just show you the whole diagram, this is a complete solution to that problem. This is a tour because you can see it's crossing every single square. Alright, so that's the setup. Now what are the questions? And first of all, they tell us that n is going to be even, at least in this part of the question, or these parts. And we're going to show with the aid of a diagram how a tour can be drawn in any n by n grid. Now I struggle a bit with explaining to you my own thought process here. Only after a very brief time I could see a way that I could always construct a solution, a kind of standardized solution for any n by n grid, but I'm not sure how clearly I can explain to you why this particular solution is the one that jumped into my head. So it'd be kind of interesting if you have a different experience in trying to answer that, or have the same experience as me. I suspect everyone would think of it the same way, but I'm not actually sure. So let me try and draw what I think is a good answer to that question, more or less. I'm going to try and draw a square. It probably won't be exact. Now, I'm not going to mark in the sub-squares, what you might call the cells, inside there, because we're considering the general case of any even value of n, so 2 or 4 or 6. Actually, maybe that's a good way to start the question, is to think about n equals n equals 2. Yeah, n equals 2 would look like that. So in order to solve the problem here, you see it's kind of trivial. You can just go like that. When you move up to n equals 4, though, it becomes a little non-trivial, doesn't it? Let me see how easily I can draw that. So I need 3 vertical lines and 3 horizontal. Well, that's not very good, is it? 2, 3. So how would we solve the problem here, ignoring their given pattern, which is obviously chosen to be quite random? Well, you sort of think to yourself, well, I want to cover everything, but I can only go horizontally and diagonally. So the natural thing to do is to choose a whole row or a whole column first, and then think, well, how can I get back to the start? I clearly can't go there all the way across, all the way around the boundary, because then I'm missing the middle. So how do I avoid missing the middle? And to me, the obvious thing to do is just to simply double back on yourself like that. So as I was just saying, I'm not really sure how to justify that, but if after a moment's thought it becomes obvious that that method will always work. So if we start in one corner and we go to the next corner, obviously it doesn't matter left or down, and then we describe half of the boundary, all we need to do is for each succeeding row above that, we simply need to double back on ourselves. and that will always work now, however many rows and columns there are, whatever the value of n. So this works for all n, and because we can see that we can, for all n which is even, I guess this is the real point of the question, which is that for each pair of rows, or each pair of columns if you do this rotated 90 degrees, we end where we start. So for each pair of rows, we can end where we start. So if you want maybe a better answer to that, maybe you can look in the mark scheme, or at least an alternative answer. It is fairly obvious, but there might be a better way to express it. Anyway, so that's the first part. Now the second part, is a tour possible if the start-finish point is changed so that it's not the top left corner? Is that what they said? Oh yeah, top left corner. So this was a solution for any even n by n grid starting and finishing in the top left square. What about if we choose a different square as the starting point? Justify your answer. Is it still possible? Justify your answer. Okay, assuming you've tried this before or you just want to listen to the answer, it is trivial that if we change the start endpoint to any other square, such as here or here, and by the way, I haven't drawn in the boundaries here. This is actually a 6 by 6 square, isn't it? Just like the one on the diagram. It's they're both 6 by 6 grids, because you can see here I've got 1, 2, 3, 4, 5, 6 rows, so I must have 6 columns. And by the way, of course, this would also work if it was n by m, at least this particular solution for even values of n, but that's completely outside the scope of the question, so we'll forget that. But anyway, on to part 2. Part 2 is answered by what's marked in red here, that if we choose a different square, maybe it's easier if you look at the neater diagram that they've drawn here. If we choose a different square, excuse me, this pen problems. If we choose a different square to start from, suppose I start from here, you can see that exactly the same route, it would be possible to get a valid answer by travelling that route. So that's the answer, and you can write that in any kind of form of English you like. Let's see, what would I write in English there? Let's go back to black. So for part 2 I might write just move the so using the same shape as for part 1, we can start and therefore end at any other square on the path, or any other square in the tour, I should say, using their terminology, in the tour. Yeah, something like that. Okay, part 2 was very easy if you just take a moment to think about it. Now something a bit different. Suppose a robot is programmed to move along a tour of an n by n grid. The robot understands 2 commands. Command R turns the robot clockwise through a right angle. So if we give the robot, let's mark the robot as that. If we give it a direction, then we're saying 90 degree clockwise rotation can of course move it to any any one of the 4 cardinal directions, if we think that way, north, south, east, west. So we've got that command. We've also got the command move forward 1 square. So in this, since it's pointing upwards, that would mean move forwards 1 square that way, or move forwards 1 square to the right, or move 1 square down, or move 1 square to the left. So hopefully it's pretty obvious what they mean there. There's actually a whole class of these type of questions used sometimes in, I think, studies in I don't know, maybe computing or IT or just mathematical logic. I don't know. Think of this idea as an automata or a robot that follows a fixed set of rules. Anyway, so what are we saying? The robot has a program, a list of commands. So a list of commands may be, for example, this is just in case you're having trouble understanding this. Something like that. So it means turn clockwise 90 degrees, move forward once, move forward twice, then turn clockwise 90 degrees and turn clockwise 90 degrees again, which means of course to turn 180 degrees. In fact, you would never do that in this particular task, would you? Because that means you would be going back on your same route. But that's what they're describing. Now there's a total number of times in the list that R appears, and they call that little r, and there's a total number of times the command F appears, and that's little f. Now what's the question? The question is, initially the robot is in the top left square. Before I go on, let me just move this. Perhaps I just do a select tool here. It's just, oops, does that work? No. There we go. Let's move that up. So the question is, given these types of commands, let's say the robot is at the top left square as before, pointing to the right, and the first command is an F, which means it's a forward motion. Then what is the value of F? What is the total number? So let's translate this part into English as best as we can. What does this mean? What is the total number of squares moved through in the tour? Okay, so can you see what the answer to that would be? Excuse my handwriting, it's terrible, isn't it? Well, you should realize that the total number of squares moved, which is the value of little f, is n squared. And in case that's not obvious, just think of the simplest possible case, which is we move once, we move twice, we move 3 times, we move 4 times. Yeah. So the number of moves is equal to the number of squares, and it must be if we do indeed traverse every square in the tour as we do according to the rules of a tour. So f is definitely n squared, so that's fair enough. Now what about, why is r plus 1 a multiple of 4? So remember, what is little r? Little r is the number of rotations So let's write this again in English. What is the number of rotations? Well, let's be specific. Number of 90 degree clockwise rotations in the whole tour. And they give you a big hint, of course, because they tell you what the actual rule is. So all you've got to do is work out why that specifically should be the case. So the first thing you should think is, well, 4 is obviously meaningful because a 90 degree rotation times 4 means 360 degrees. It means we've gone through a whole circuit. So obviously when r becomes, like, for example 9, it means we've rotated 8 plus 1 times, which means we've rotated all the way around twice plus another once. But why specifically should this number be, or let's say, why should the number of rotations plus 1 be equal to a multiple of 4, meaning that the number of rotations plus 1 should result in the robot having the same orientation at the end of the tour as at the beginning. So that means we should think about the end of the tour and the beginning of the tour. So what's common in all cases for the end of the tour and the beginning of the tour? Well, let's say the end of the tour we have this rotation. What orientation do we have at the end? Well, I hope you can see that especially since they told us that the actually, did they restrict this to the case of starting in the top left corner? Yes, they did. I think it works anyway, or it's similar, but let's just keep it simple. If we're starting in the top left, then we leave going that direction. But how do we come back? Well, I hope you can see we must come back in that direction, because we're not allowed to move along diagonals. That's not in the rules. So we must come back there, which means final orientation is plus 270 degrees from, that's not from, is it? That's for, from starting orientation. Therefore, R from the initial position is the total number of degrees rotated around, plus 1 would end us having the same orientation as start. So finally we get the required result that R plus 1 is a multiple of 4. Let's just say 4k, where k is an integer. So R plus 1 is divisible by 4. Alright, what's the next part of the question? Number 4, part 4. Must the results of part 3, those two deductions, f equals n squared and r plus 1 equals 4k, must they still hold if the robot starts and finishes at the center of a different square? That's a good question. Think about that. So, if you're ready, well, let's think in particular about, well, let's think about both of them, right? First of all, is this still true? I hope you agree that it is, because we still have to move through every square in the tour, and so obviously that's all squares, so that's n squared. So that part hasn't changed at all. But what about this orientation argument? Did this orientation argument that we made here depend on the starting and ending point being in the top left corner? Well, it kind of did, didn't it? Let's take an example. Let's go back to our earliest thinking here. We saw that a tour could be made to be valid, such as this tour here, starting at any particular square. We could start here, we could start here, as I indicated before, or here. Now let's suppose we started here. That means our initial orientation was that way. Well, no, it doesn't mean that. It could mean that. It could mean our initial orientation was, let's say, eastwards. And that would mean that our final orientation would also be eastwards. So in that case, the difference between the starting and initial orientation is 0 degrees, not plus 270 degrees, as we had in the previous case. So we can say, but r plus 1 divisible by 4, not always true. If, let's say, if path through start endpoint is a straight line. And we can see that in that case, r is divisible by 4, because it means that the orientation at the start and end are the same, which means that r is divisible by 4, a multiple of 4, we could say. Okay, so we're nearly finished. I think it's just the last part now. So I hope that reasoning is clear enough. Obviously my handwriting is not great. I'm not hugely brilliant at writing on this machine at the moment. But see if you can polish these arguments, maybe add a little detail if you like. But to be honest, this question is not as hard as it seems. So you probably don't need to write a huge amount. Now the last part is probably the most interesting part. because it really requires you to kind of think out of the box a little bit. The last part says, show that a tour of an n by n grid is not possible for odd values of n. Okay. Now, as is so often the case in these more advanced questions like STEP and MAT, especially STEP, you've got this delicate, this delicate balancing act to do, where on the one hand you must, so to speak, respect what you've already learned in the question, but on the other hand you might need to go significantly beyond it, and it's always difficult to know how much of the solution to the final parts of these questions is dependent on one or the other. So let's quickly review what we've learned so far. We learned the definition of a tour. We learned that we can, for even values of n, we can always make a tour, such as the one I showed on the left diagram here. We learned that it doesn't matter how to put it. We learned that you can start and end the tour at any point as a trivial consequence of the fact that as long as the tour exists, you can move the start and end point anywhere. But then we learned something interesting in part 3 and 4, didn't we? That there are these formulas for F and for R, which are the number of moves we make and the number of rotations we make. So we have to think a little bit more in depth here. Now I'm trying to remember my reasoning as how I got to the answer. There's some sense in which the first diagram I drew gives us a big clue, I think, that this process clearly would not be possible. Yeah, that was it. This process would not be possible if I added an extra, let's say, 7th row and 7th column. So if I sort of added another row and column here. Why would it not be possible? It would not be possible because when we reach this point here, we somehow have to go back up and then include all the points on the squares on the 7th row. Oh, by the way, if it was 7th, you'd need to go like that. Yeah, but that wouldn't change anything. But in order to include all these rows, you'd be stuck because you wouldn't be able to then suddenly jump back to the beginning. So that gave me a clue that I'm thinking about how many steps I take rightwards or eastwards perhaps compared to how many steps I'm taking westwards. And of course east, west and north, south are totally symmetric in this problem. There's no relevance there. Okay, let's call it left and right and up and down, not east and west. So the germ of my idea was it's probably the case that I can prove it's impossible by noting that the number of steps to the right and the number of steps to the left must be equal. And I look also at this more random example to see that the same kind of principle is applying, right? If I were to count all the steps to the right, they must be equal to all the steps to the left because my final position is the same as my starting position. And the same is true of up and down. So it's a kind of a conservation principle idea. So how can we write that? We can say x equals steps to the left, y equals steps to the right, and let's give two other variables, a up and b down. And what we observed is because, hopefully you can see that, because start point equals end point, it follows what equations follow. Can you tell me? Well, it follows that x equals y and that a equals b. Now, this observation in itself doesn't prove anything much. But then we think, okay, can I combine this with what I already know? And then it suddenly clicks, yes I can. Because if we look at f f was the total number of steps, and we know that f is equal to n squared, but the total number of steps is equal to the sum of those 4 variables I've just written down. And since x is equal to y and a is equal to b, we have 2x plus 2a, let's say, or 2x plus a. So if we assume that n is odd, we see there is a contradiction. Because if n is odd, such as the number 3, you get 3 times 3, you get an odd number, and the right-hand side is even. Okay, so you can write that more formally as a proof by contradiction, let's say, but we have created a contradiction by observing that if n is odd, whoops, I don't quite know how that happened, excuse me. Yeah. So we have observed that if n is odd, there is a contradiction, and it's impossible to create a complete tour. So that's the completed answer for number 5. I hope you found that in some way interesting. See you next time.